and I'm going to let Dr. Kevin Bai introduce himself. So thank you, everyone. I hope you had a great weekend. I'm actually going to turn off my camera. And if you are watching from home, you do not need to have your camera on unless you're Dr. Bai. And I'll let him introduce himself, and then he can give his talk. I think this will be really good.
Okay, thank you, Anne. So my name is Kevin Bai. I'm an associate professor in University of Tennessee. I studied in Tsinghua University for my both bachelor and PhD degree till 2007 in Beijing, China. And then I came to University of Michigan Dearborn as a postdoc. I joined Catholic University, the former General Motors Institute in Flint from 2010 to 2016. So at that time, I was that was the first time for me to really explore the electric vehicles. To be honest with you, before 2010, I was not a vehicle person at all. I was really thinking of wouldn't be nice if I don't have to drive. Actually, as a matter of fact, some experience to share with you was in 2007 when I first began to drive. I went to a dealer to find a car. And the dealer told me, okay, here the car is yours, so you can go ahead to give a try. My question was just, okay, how am I supposed to do that? So he handed me a key, and at that time I didn't know that the key is supposed to be used to start the car at all. But after many years in the electric vehicle areas, I found out that the vehicle really is a very multidisciplinary, very complex, and also very interesting objective to really work on. I have a lot of automotive friends in Michigan, and some of them are really proud of themselves because they actually said, Kevin, if you look, you can teach multiple courses, but whether students like your courses or not, it's really up to them. You cannot see. You cannot know. Maybe sometimes you will do some survey, but not everybody will really like the products you provide. But look at us, we provide a new type or new model of the car. The next day, probably we will see the car we designed really run on the road. That really make myself a very proud person. I think that's pretty much true. From the vehicle point of view, because it's too complex, it's very difficult for us to cover all the aspects. Therefore, in the vehicle companies, you can see there are a lot of departments. Some people are in engine, some people are in energy storage, some people are in sensor and radar, and all the departments, all kinds of departments, thousands or tens of thousands of people will have to work together to really make the car work. So that's a really amazing part. For today, I'm only going to cover some elements in the hybrid electric vehicles or electric vehicles. Why do we want to do the electric vehicles? One thing is, if we look at 3 years ago, how we spend the energy, or use the energy in the country, we have a bit of solar, we have some nuclear, hydro, wind, natural gas, coal, and petrol. You see, even though we have been devoting ourselves to the renewable energy for many years, still the dominant energy sources are petrol, coals, and the natural gas. So there's three things, three elements. And also, if we look at where do all this energy go to? Okay, this energy goes to the electricity generation, goes to the residential, commercial, industry, and we find nearly 30% of all this energy goes to the transportation. And what makes things worse, or I would say better, is if you look at how much energy really is becoming rejected energy, meaning the heat or the wasted energy. Among 28% of the all energy spent on the transportation, 22% is becoming the rejected energy. And only we use 6% of the energy. You can use all this energy to drive your vehicle. So in other words, probably the efficiency of your car is about 5.91 divided by 5.9. That's about only probably 20% efficiency. So the reason I say it's bad is because you see how much energy we really wasted by driving the car. But the reason I say it's good is we see the potential, right? There is a huge potential here for us to improve the energy usage in the vehicle. If you can improve, let's say if you can really help us to save 10% or recover 10% of all of this, of all of this 22% of the energy wasted, then you are talking about maybe 40% efficiency improvement for the overall transportation. That's really an amazing part. So this is why the electric vehicle or hybrid electric vehicle is coming to secure or to recover this part of the rejected energy. Okay, but of course, if we are working on the car, there are so many things for us to really talk about. We can use a model to simulate the vehicle dynamics. We can design the battery, design the battery pack or ultracapacitors used in the vehicle as an energy storage. We can also talk about the mechanical or aerodynamic design for the vehicle to yield better, I would say, the less air drag, thereby generating higher efficiency. Or we can do the battery modeling and talk about the regenerative braking, control and power management. Right now, the autonomous or connected vehicles are coming. Therefore, radar and sensors are a hot topic. Of course, for today's most of the electric vehicles, the key enablers are power electronics based motor drive system, battery charger, and the electric machines on the vehicle. Okay, so there are so many areas we can really cover in the vehicle. Therefore, vehicle is really an industry influencing a lot of, or I would say, creating a lot of job opportunities. Especially if you look at about 10 years ago, if you look at the majority of the universities in US, there were no power electronics, no such course at all. So there were probably several universities having. But after this electric vehicle is brought up into the agenda, everybody find out they need to convert the battery energy from the DC to drive a three-phase motor on the vehicle. Therefore, they need a DC to AC converter, which is enabled by power electronics. Then they find out, okay, they need to charge the battery on board, which converts the AC grade energy to store it in the DC battery source. Therefore, they need an AC to DC converted battery charger. Okay, and then the electric machine. The electric machine really is a very old industry. Think about we can talk if we talk about how the electric machines are coming. Trace the origin of the electric machine back to more than 100 years ago. A lot of people believe that machine design is already pretty mature. There's really nothing to do in the electric, or no innovation to do in the electric machine. But then the electric vehicle comes to say, I need a higher efficiency, but I also need a smaller size. And more importantly, you have to make it cheaper. Therefore, everything, all the challenges come to the vehicle to bring the new demand, thereby generating, I would say, triggering more the motives of the innovation for the electric vehicles. Okay, so if you talk to an industry, to talk to an automotive person, usually they will say, I hope you give me a device, I hope you give me equipment, which is very reliable, very small, very light, and most importantly, very cheap. So when you place all these specifications or requirements on the table, you will find you will challenge yourselves to the end. You will really corner yourself to the limit to say, okay, what type of design, what type of device I have to select, what type of topology, what type of the packaging, what type of the cooling system I need to design to make it reliable, make it high performance, and make it cheap. Now, if we only look at the I would say, the bulky part to enable the electric vehicles. We need the power electronics. This power electronics is mainly to convert the battery, which is usually located on the back side of the vehicle, which provides a DC to the AC to drive a AC on the motor, to drive a three-phase AC motor in the front. Okay, and you also have the engine. Okay, so sometimes you have the engine if we are talking about hybrid electric vehicles. Now, if we are talking about the pure electric vehicle like a Tesla, we don't I think the vehicle Anne is driving, the Nissan Leaf, they don't have engine. The only battery, the energy source is from battery to drive power electronics and drive the motor. Okay, so you place a heavy battery on the back. You place other heavy part like power electronics and motor in the front, so you have the better balance. And originally, you can pump the gas at the side of the back side of the vehicle. But right now, if we are talking about the pure electric vehicle, you don't need a fuel anymore. Therefore, you just plug in the grid to charge the battery. Okay, so you have the battery charger at the end. So really, from the electronics point of view, we see there's a charger, there is a motor drive system, which we call it an AC to DC converter. There is a motor, but more importantly, we have the battery. Okay, in recent years, we find the electronics part becomes cheaper and cheaper. The electric motors cost also drops significantly. But right now, the bottleneck, it comes to this battery. Okay. Now, overall, if we start talking about how all these parts work together, okay, there are several architectures for the electric vehicles or hybrid electric vehicles. The first part architecture is called a series architecture. So series means, so I actually mentioned this many times for the students, that series doesn't mean the battery and the motor are in series, okay? The series really means the engine and the motor are in the same loop. So in other words, engine will rotate to drag the generator. Generator generates three-phase AC received by a rectifier to rectify into the DC. If you were in the ECE 300 level class, like diode talking about the diode MOSFET, you actually know there is you can use the diode as a rectifier to convert the AC into the DC. Of course, in the vehicle, the rectifier usually is much more efficient than only using the diode. So you can rectify it to a DC, then DC drive an inverter to this motor controller, convert the DC into three-phase AC to drag a motor, then drag the vehicle. Okay. Then meanwhile, you have a DC to DC converter connected to the battery. If you are talking about plug-in hybrid electric vehicles like Chevy Bolt, then you will have the battery charger. If you remove the battery charger, then the whole vehicle is just a very simple hybrid. Okay, so when you are driving the motor, you rotate the engine, provide the energy through the generator to rectifier, to motor controller, to traction motor, then drive the vehicle. Okay, and if your battery is has enough energy, battery could also kick in, work with engine together to drive the motor and drive the vehicle. If you find your engine is not efficient, very efficient, or there's no use for the engine, for example, if when you are braking your vehicle, you are decelerating your vehicle, you can shut down the engine, the kinetic energy of the motor will be converted back and stored in the battery. Okay, so, and again, in this architecture, the motor and the engine are in the same loop. Therefore, we call it as a series architecture. And again, we talk about the engine and the motor relationship. The typical example is Chevy Bolt. Second architecture is called a parallel architecture. So parallel means the engine and the motor are in parallel connection. So engine can drive the whole vehicle. You can also use a battery to drive a motor. Usually the engine and the motor are connected through a mechanical coupler or a pulley. And coupled together to drive the vehicle. The typical example is a Ford Escape hybrid electric vehicles. Okay, and also in Ford Escape hybrid, this battery is a pretty small battery. You do not count on such battery to drive the whole vehicle at all times. So the battery is like an energy buffer to provide some auxiliary power to the engine, or to choke the regenerated energy back to the battery. The third one, which is also existing for a long time, is Prius. Okay, the Toyota Prius. The architecture they are using is called a series and parallel architecture. Now, if we are talking about, let's say, Nissan Leaf or Tesla, what we need to do is only having a battery and a motor. And in the middle, of course, you need a power electronics converter to convert the DC into three-phase AC to drive the vehicle. If you, some cases, you might need a gearbox, okay, some gearbox to convert the motor speed into the vehicle speed, okay. And now we can build a pure electric vehicle. Then the engine and generator exist. Engine, the generator, and the battery are connected through a planetary gear, a gearbox. Okay, this gearbox contains ring gear, sun gear, 3 gears. Okay, and the engine. So, for example, in this layout, basically I can lock any gear and let the other two work together. Now at the end, I can introduce another gearbox, okay, to connect the ring gear with the motor together, okay. So let's say right now I have an engine, I have a generator, I have a battery, and I have a motor, okay. Now assume if I'm going to lock one of the gear, for example, I lock the engine, I just shut down the engine. So in this middle is this gear, this green part does not rotate anymore. But I can still use, let's say I can still use which part? I can still use the battery, okay. So I'm going to use the battery to rotate the motor. Meanwhile, I can also use the battery to rotate this generator. So the generator becomes like drive, okay. Then this battery actually rotates the middle sun gear. Sun gear eventually through the green box go to the ring gear and provide the power, okay. So now the relationship between the engine and the motor are not a simple series, are not either series, nor a parallel relationship. Therefore, we call it as a series and parallel. The key part is this planetary gear, planetary gearbox, and of course, such design usually is more complicated. Therefore, a lot of vehicle companies do not really favor this design. They feel like I need to really introduce a planetary gear and a multiple gearbox. And eventually the control becomes quite complex. Okay, so these are basically 3 structures of the electric vehicles. Now, when we look back to say the electric vehicle history, okay, we have been developing so many structures. The electric vehicles, this concept really is not so new, okay, where the vehicle can be traced back to 1885 when the first vehicle was invented. And in 1914, Henry Ford and Thomas Edison was even talking about the electric vehicle at that time. People were very passionate at the electric vehicle first. Then when the engine technology comes, people find actually electric vehicle is comparably expensive than the engine vehicle, the gasoline vehicle. Therefore, the electric vehicle has been silent for many years. And also at that time, is electric drive new? Actually, this technology is not new at all. So in 1914, Oliver Fritzley, as a chemistry, patented the battery. You think about, some people say, well, battery is a fascinating stuff, but the battery was first patented more than 100 years ago. He also patented as a chemist, that's a fascinating part. As a chemist, he patented regenerative braking, okay, and a hybrid powertrain. So in some, so I still remember in some conferences, people say the electric vehicle is so fascinating. You can really do a lot of regenerative braking. You can harvest the energy from the wheel to stored in the battery. But this concept, you see, has been patented more than 100 years ago. And to make things more fascinating, Oliver Fritzley, back to 100 years ago, has already driven his car, electric vehicle, for 1,800 miles between Lincoln and New York in about 100 days. Everyday travel 90 miles per battery charge. Okay. Is battery charging new? No, actually, again, back to 1914 or 1912, we already have the battery charger, even though at that time the charger is not very efficient. Okay, so we can, and also at that time you cannot really have the smart charging. We usually use a hand cranked battery charger. So at that time there was even no diode. So the charger usually is pretty bulky and pretty inefficient. But the charging, EV charging, is already doable at that time. The bottleneck so far is really the battery, how to manage the battery on the vehicle. Majority of the battery we are using, if you heard from the news or read from some website, usually the battery cells we are using in the car is lithium-ion batteries. And the lithium-ion batteries voltage usually is about 3.7 volts per cell. Some of the battery, like a lithium iron phosphate battery, is about 3.3 volts. Now, in order to build a 400 volts system, you probably need many cells in series connection. In order to provide a huge current to the motor, you probably also need a parallel many. In this case, you will find many cells in parallel and the series connection, which actually lowers the reliability of the battery pack. Okay, it's very reasonable for us to think, okay, imagine if one cell suddenly fails. If one cell is failed here, let's say it's open, then the whole string cannot be used. If it's short, then you will create the voltage difference between two strings. Eventually, there will be some circulating current in between. Okay. I'll give you one example about the Chevy Volt. Okay, when the first Chevy Volt came in 2012. Okay, so Chevy Volt used the 288 cells, the lithium-ion cells. Okay, this cell, 288 cells together. Okay, now when the battery comes, when the first Chevy Volt comes, the Chevy Volt price is about the market price was about $40,000 per car. Now, in order to fabricate the whole vehicles, the cost is about $60,000 per car. So that means to sell one vehicle, GM will lose $20,000 per vehicle. Okay, the key point is, first is this cell. This cell is super expensive, and to make it even worse, this cell is very fragile, so you cannot let it overheat it. When it's overheated, the battery will age very quickly. But when it's underheated, let's say the temperature is pretty low, then the battery chemical reaction inside will become very sluggish. Therefore, we need a coolant. So each cell will have to be attached to a heat sink. This heat sink is, to fabricate this heat sink, each heat sink is having nearly the same cost as the cell. Okay, so you think about, you need an expensive battery cell. You need a quite expensive coolant system. And that's not all yet. Later we'll talk about, we even need more battery management system. Okay, and this is why actually at that time there was a debate: is a lithium-ion battery really the answer for the electric vehicle? It's so fragile that you have to carry it very much. Okay, and the voltage is still not high enough, so you have to series them and parallel them. The management system probably is as expensive as a battery pack. Now, once you package all the cells, 288 LG pouch cells together, this cell is about 800 pounds. So that means when you before you put your before you drive the vehicle, you already add multiple persons on the car already. Okay, this cells is about I would say probably the size, it is about an adult size like me. Okay, so you have two wings and a pretty long cell here. And when using these batteries, there are some problems. First, the challenge is the imbalance in the voltage. Okay, the voltage and state of charge among the cells are imbalanced. Secondly, there might be some imbalance in the temperature, so you need to manage. Okay, for example, if I'm going to let the coolant flow from one to the end, it's quite reasonable for us to think of maybe in the very beginning, the temperature is low. But once the coolant travels to the end, maybe the cells at the end probably will have higher temperature. So there will be some imbalanced temperature in between. Now, even though we make everything the same, let's say the battery voltage, state of charge, current, temperature, thermal, everything is balanced very well. Still, when cell was fabricated, there will be some diversity in between. So eventually the cells will diverge with time. Some cells age faster than others. Okay, then we have to manage it well. Otherwise, if we just leave it alone, that cell probably will age very quickly, then at the end fails, thereby failing the whole string or whole pack. Okay. Now, we mentioned in the previous slides, there is a concept called a state of charge. We learned I think for all the REU students, you learned the circuit one. Okay, so you know what is a voltage, what is a current, and maybe you also have some mechanical or thermodynamic knowledge, so you know what's the relationship between the power loss and the temperature. But for state of charge, it might be a quite new concept. So usually in the battery domain, we don't talk about the current. Okay, so for example, in the electrical engineering domain, we usually say, okay, this equipment can provide us 10 ampere. For battery expertise or battery applications, they don't say that. They never say this one can provide 10 ampere or can provide 100 ampere. They will say this battery is rated at 1C. Okay, so in battery area, we define the discharging and charging current using 1 hour to deplete or charge the battery from full to empty or from empty to full as 1C. Okay, so in other words, if a battery is rated as a 10 ampere hour, that means you can discharge this battery from full to empty using 10 ampere for 1 hour. Therefore, 1C for this battery will be 10 ampere. 2C for such battery will be 20 ampere. 0.5 C for this battery will be 5 ampere. Okay, so this is the first concept, 1C. The other is the SOC, state of charge. State of charge then is a proportion of the charge available at the point compared to the total charge available when it's fully charged. Okay, so what does this mean? Now assume right now I have this battery is 10 ampere hour. We know ampere is a current unit, hour is a time unit, together is a charge unit. So if I say right now this battery has a 5 ampere hour charge available, that means right now the state of charge is 5 ampere hour divided by its rated 10 ampere hour. So the state of charge for the battery right now is 50%. That means this battery right now is a half empty or half full. Okay. So for battery, if we use the state of charge to evaluate is full or empty, when it's full, it's 100%. When it's empty, it's 0%. In most of cases, it will be some number in between. Okay. So in the electric vehicle, the state of charge evaluation usually is like what? It's like a fuel gauge in your gasoline vehicle. Okay, in the front panel of your gasoline vehicle, you have a fuel gauge, right? So if it goes to the very left end, you see right now I need a charge, or fuel. If is located on the very right hand, that means I have enough fuel. That fuel tank is totally full. Okay, so the SOC is the same. I would say a same parameter, so similar parameter. Except it's used in the electric vehicles. Okay. Now, when we have so many batteries and we know how to evaluate this battery by using the state of charge, then we are going to really see how this battery management system can behave to help me prolong the lifetime of the battery, or I would say the maximize or prolong the lifespan of the battery. Okay, so BMS in the vehicle will need to control the charge and discharge. A lot of people say well, we need the battery charger to control. Actually, that's not true. Okay, battery charger is a unit only to convert the AC grade to DC battery. But how many charge you want to dump in the vehicle within how long? That's not up to the battery charger. Battery charger cannot do that. Of course, battery charger eventually will convert the energy, but whether you are going to use 10 ampere or 20 ampere or 0 ampere to charge the battery charger has to listen to the BMS. Okay, so this is the first unit, the function of the BMS. Secondly, battery charger, the BMS battery management system will need to monitor each battery's status, voltage, current, temperature, state of charge, and state of health, whether this battery is healthy or not, whether it can still hold the charge. Then cell balancing. Okay, so eventually if there is some imbalance between the cells, then this is the job for the BMS to do. It also needs to prevent all kinds of hazards, voltage, let's say over voltage or under voltage, over temperature or under temperature. At the end, it will need some communication information, communication function. Okay. Imagine if I have 3 cells in series connection, I will then need 3 sensors. This 3 sensor will sample everything you can for the battery. Then send this one to the model and to say, okay, compare with a model whether this battery is healthy or not, the other battery is healthy or not, whether they are balanced or not. If they are not balanced, then your controller will have to do something to make it balanced. Okay, so that's an overall high level layout of the BMS. Now, when we balance the battery cells, usually there are 3 categories: resistor balancing, capacitor balancing, and inductive balancing. Resistor balancing is very simple, very inefficient, but very cheap technology. Therefore, right now, nearly in I wouldn't say 100%, but a majority of the electric vehicle companies use resistor balancing. Okay, if you learn the MOSFETs in the in your 300 level class, this layout, you will find this layout quite simple. Now we have 4 cells here in series connection, and to balance them, I will assign 4 MOSFET to the cell. So I will monitor all the voltage of the cell. If I found, okay, let's say the first cell has a very high voltage, I'm going to turn on the controller, will turn on the first MOSFET. Once the MOSFET is turned on, you can treat it as a short circuit. So the first cell will be able to dissipate its excessive energy through the resistor. Therefore, we call it as a resistor balancing. Of course, once you short the MOSFET, this battery, high voltage battery, or higher voltage battery will dissipate its energy, thereby dropping its voltage. Okay, so it's quite affordable. It's quite simple, even though at the end, all this energy will be dissipated through the resistor as a heat. So the efficiency is horrible. At the end, you cannot enable this battery, you cannot enable this balancer at all times. If you turn on one cell, let's say the MOSFET at all times, then this cell will keep dissipating the heat. Eventually, the resistor, not only the cell, but also the resistor will be heated up. Now, second one is called capacitor balancing. Capacitor balancing is definitely more efficient than the resistor balancing, but it has its own problem. So to build such a battery equalizer, you will need multiple, let's say you have n cells, then you need n-1 capacitor and n double throw switches. Okay, so let's say if B1 has higher voltage than B4, for resistor balancing, the rationale behind it is to let's dissipate the heat, the energy inside of B1. For capacitor balancing, the rationale behind it is let's try to use a capacitor as a buffer to transfer the energy from one cell all the way down to another cell. For example, if I parallel CE1 with B1, then you will store the energy to CE1. Later on, I parallel CE1 to B2, then the energy will be transferred to B2, so on and so forth. At the end, you will be able to transmit or transfer the power from B1 from all the cells. All the cells at the end will have the same voltage. Okay, but usually to do this, you need a large size capacitor. So capacitor is a challenge, and also how to build these double throw switches. That remains another topic. Inductor balancing is another way. If we don't use, think about in the circuit one, you learned three major passive components: resistor, capacitor, and the inductor. If I don't want to use a resistor, capacitor, maybe I can also use an inductor. Okay. For example, if I say that I right now have 2 cells, okay, so I'm going to transfer the energy from first battery to the second battery. What should I do? I can turn on the top switch, so let the battery store the energy into the inductor. So your inductor will store some energy. Then I can shut down the switch. The current of the inductor cannot go through this switch anymore. Therefore, the current in the inductor will have to find some path to go. So the current will go through the battery to charge the battery, then freewheel through the diode. Therefore, this will successfully transfer the power from one cell to the other cell. Okay. Now, of course, if I have, this is only 2 battery cells. What if I have so many battery cells in series? Okay, so this is another concept brought about 10 years ago called multi-winding transformer balancing. It's also an inductive balancing because you can treat the transformer as a combination of multiple inductors. Okay, so now, let's say, how is this circuit supposed to work? I can do this. Let's say right now, I have 6 cells. Then I will make a 6-winding, I would say 7-winding transformer, 1 on the primary side, 6 on the secondary side. Then 6, each winding will connect with the battery cell through some switch. This switch can be a MOSFET. Okay. Now I found, okay, the cell 5 has a pretty high voltage, higher than others, but I don't want to dissipate it as a heat. What shall I do? I can turn on the switch S5, and I turn on the switch. So I will parallel this winding with battery 5. So the energy will be keeping stored inside this winding 5 on the secondary side. Now, later on, I will turn off this switch and turn on the primary side of pay attention, there is another switch on the primary side. I will turn off S5 and turn on primary side. You have stored enough energy. This energy has to find some way to go. Okay, so this energy will actually go through this core, cross the core, induce the energy to the primary side. Okay, the energy will travel from secondary side to the primary side to charge the overall cell, overall pack. So in other words, what this inductive balancing doing here is first store the energy in the cell, in the winding, in the related winding, then use such energy to charge the overall pack. So that in this way, it will redistribute the energy, excessive energy from one cell to the overall pack. Okay, so at the end, you can do such operation to whatever, or whichever battery cell you feel needed to be balanced. Okay, the efficiency definitely is much better than resistor balancing, because ideally, if there is no loss in the transformer, of course we know that's not true, but ideally, if the transformer can be designed very efficient, then you can deliver this energy with very little loss. Okay, instead of dissipating as a heat in the resistor balancing, you actually redistribute it, reuse this excessive energy and distribute it to other cells. Okay. There are other applications for the battery balancers. For example, the previous one, you feel, okay, I need a lot of windings for the transformer. Maybe this transformer is very difficult for me to make, or maybe the cost is very high. So we can introduce another balancing called power electronics balancing. Okay, so let's say still we have 6 cells. Okay, I will place a DC to DC converter, okay, in the middle between the whole pack and any battery cells. In addition, I will introduce, let's say if I have N cells, I'm going to introduce N multiply 2 switches on the primary side. Okay, so now let's say I assume right now my battery 6. Okay, battery 6 has a pretty high voltage. I don't like it. I want to dissipate it, this energy, but I don't want to dissipate it as a heat. So therefore, I want to redistribute this battery 6 energy to other cells. So what we are going to do here is turn on 6 plus and 6 minus. So you see the positive connected to one side of the DC to DC, and the negative connected to another side of the DC to DC. So in this case, this converter's left side is connected to battery 6. The other side of the converter is connected to the whole battery pack. Okay, so now you bridge the high voltage battery 6, high voltage battery cell 6 to the whole pack. So this bidirectional to DC to DC converter's job is to convert the DC energy of this battery 6 to charge the whole pack. So in other words, battery 6 will donate the energy through this converter to charge the overall pack. Okay, of course, battery 6 will lose most of the energy, receive a little, while other cells don't lose any energy, but receive the overall energy. Okay, so at the end, this battery will be balanced. Okay, This to build such a converter is easy. You don't need that multi-winding transformer anymore. For anybody learning the DC to DC converter or power electronics, this converter is just a piece of cake. Okay, but the thing is, you will need to introduce 2 multiply N switches here. So that probably will be the cost-driven part. Another part of the balancer you can do is, instead of using the whole pack, you can do this. You can split the whole pack into 2 parts. Okay, let's say right now I have 100 cells, so I can split the first top category or group, the first top 50 cells as group A, then the rest as group B. Okay, and so I say right now I find A2 has a high voltage, let's say B3 has a low voltage. So I need to deliver the energy between A2 and B3. Therefore, in the middle, there's a DC to DC converter. And this DC to DC converter, left side will receive A2 voltage. Right side will receive a B3 or B3 voltage. Since their voltage are quite similar, so this DC to DC converter design is also simple. Okay, it's much simpler than the previous one, because the previous one, think about the right side will have to undertake 6 cells, left side undertake only 1 cell. So the ratio, voltage ratio is about 1/6. This design, left side and right side nearly have the same voltage. So you are talking about a 1-to-1 ratio DC to DC converter design. Okay, we don't have the time to talk about the converter design, but usually 1/1 design, such ratio is more pleasant than 1/6 or even 1/60, such kind of absurdly high turn ratio. Okay. Now we have talked about how this converter, how this balancer has been working from the theory point of view. In reality, actually on the market, we can find this battery balancer already. Okay, it's very amazing to see how the market can be mature very quickly. Okay, like LT, they have the resistor balancing. You can balance about 12 cells. So you see there's a S2 to drive the MOSFET and connected with the cell. C2 and C1 together will measure the voltage. If this voltage is too high, the chip will eventually turn on the MOSFET to let the cell dissipate through this 33 ohm resistor. Okay, and again, this resistor is up to you to configure. If you want to dissipate it faster, you can give a 10 ohm or even smaller resistance. Okay.
So is this just a giant IC? Like, how big of an IC would this be?
Yes, it is a giant IC. I don't know how big it is, but here is a IC part number. Okay, so later I can share these slides and you can search this part number through DigiKey. I remember back to 2008 when I was a student, people can still publish this such kind of applications in the journal paper. But then back to 2016, when I was supervising a REU student doing their capstone project, they have already been able to acquire such IC from LT and build a capstone project. So definitely you see how fast it can be just from the laboratory application moved to the capstone, or there's something you want to do for fun.
Pretty cool.
And TI also have the similar chip. Okay, but this chip probably is already old, but this chip can overall balance about five cells. Okay, it's also a pretty. It is also an IC. Okay. LT also, the previous 2 examples are resistor balancing. LT also have an IC to even control or some I would say the active inductive balancing. So for example, like this LT8584. Okay, so if it turn on the switch inside, the battery will store the energy in the winding. Okay, in this winding. Now, if we turn off the switch, the energy stored in the winding will be transferred to the secondary side, then charge the overall module. You pay attention, module plus and the module minus is here, module plus and module minus. In other words, this chip is already able to store the energy, to choke some energy from one cell, then deliver it to the whole pack. Okay. All right. So that's an overall of overall examples. If you are interested in this, you can go ahead to search all these chips. So future research for the battery balancer. We have been frequently asked, can we really skip the balancer or BMS? I would say probably not, because even though the technology or manufacturing technology of the battery is improved a lot, still we cannot guarantee all the cells will age at the same speed. So we still need some BMS and the battery balancer to do its job, to do its duty. But we could definitely make the balancer more efficient and more affordable. For example, I can have some better design, innovative design for the transformer, or maybe I can make the switch faster and more efficiently, thereby saving some loss. Okay. Enhance the battery quality is definitely the key. And again, so for example, if really we can guarantee the battery are all identical, then we don't need the balancer. But right now we can't. Therefore, we will need some efficient and affordable balancer. Affordable is another important thing. As we said before, we probably cannot give automotive company a very fancy, very efficient, but a very expensive approach. This explains why the resistor balancing is still having its market. Okay. With that, I think I'm going to wrap up my presentation and probably leave about 5 minutes for the questions.
I have one question.
Yes, please.
So for the inductive balancing, you're using batteries to and transformers.
Yes.
To transfer the energy, but don't transformers only work with alternating current? So how would the battery provide the AC?
That's a good question. So when you learn in your 300 level class, usually, let's say the transformer you are talking about is 60 hertz transformer, and it can transfer the energy from 160 hertz AC to another 60 hertz AC. So you can step up or step down the voltage, right? But essentially, we need a view transformer as a combined two inductors. Okay, the energy transfer doesn't have to be AC. Okay, there is no such conclusion to say it can only accept AC. Okay, what we learned essentially is the variable flux will induce variable electricity.
Right.
Yeah, in other words, as long as there is a parameter, let's say the current or voltage, let's say current flowing through one side is a variable, it will induce a variable flux. That variable flux will induce the variable voltage at the other side.
Okay, so by switching the DC, you could transfer the energy just by switching it, basically?
Exactly. But on the other hand, you don't want to give a pure DC to, for example, if this winding always undertakes a DC voltage, okay, then the DC voltage eventually will generate the DC current, right? So if this voltage is too high, the current goes up, eventually your core will be saturated, right? So we don't have enough time to talk about this, but if we really do the simulation for this winding, we place a probe on the secondary side of the winding, And we will find actually the voltage you imposed on this winding is AC, except when you turn on the switch, it is a positive. When you turn off the switch, the voltage across this winding is reversed. The polarity is reversed because of the existence of the primary side. So it's like a choppy, pretty choppy AC positive voltage for a little bit, then negative voltage for a little bit. Overall, this voltage, I would say the average value is still 0.
Okay, thank you.
Okay.
I have a question.
Yes.
So back to the different models of like hybrid vehicles. One of them, like from your diagram, it looks like the gas, like the combustion motor, was basically hooked up to the like the electric powertrain first, and then to the wheels. In other words, like in a normal combustion car, it's just the engine, transmission, then it goes to the wheels, right? Well,
Yes.
on some of these cars, it looks like the engine in the hybrid case is like going through the electric, like the electric motor first to drive the car. That's pretty weird, I think, right? I mean, is that common? Or?
You mean this application, right?
Yeah, kind of. Like, because normally I would think in a hybrid car, you know, that gasoline would just go straight to the wheels, you know, through a transmission, but I guess that's not the case here.
So let's say if I'm going to use the engine and the transmission to drive the wheel, right? From an architecture point of view, it looks very simple and very reliable, right? But usually in that case, what's happening is, imagine your vehicle is slowing down, then your engine has to slow down, transmission slow down, right? For the engine, usually in the low speed region, if you look at this figure, as low speed region or super high speed region, the efficiency is not the highest. So the sweet spot for the engine is really a limited zone. Okay, now when the speed actually or power goes down for real quick, then your efficiency drops sharply. Okay, so this is why a lot of times if we just drive the vehicle on the high speed or medium high speed for a long time, we find the gasoline we use is pretty good. But if we are driving the vehicle in the city, we have to frequently go to this low speed region, and the engine efficiency drop, transmission efficiency drop. Usually you are talking about 15% or 10% of the efficiency, right?
Okay.
But by using such application, okay, for this layout, it seems like you add more component, but I can always make sure this engine, maybe not always, but for most of the time, I can let this engine work at this sweet spot. So let's say, imagine my vehicle doesn't need that much power, but in order to make an engine work efficiently, I have to give a lot of power, let it run to output more power. What shall I do? Well, engine can still provide, let's say 100 kilowatt power. But if the wheel only need 50 kilowatt power, I can let the rest of 50 kilowatt power go through the DC-DC and tentatively store in the battery.
So it's like not wasted, basically.
Not wasted.
Okay.
Then later on, you say, okay, I need to withdraw the energy back from the wheel. You can shut down the engine. When you shut down the engine, you don't need any gasoline anymore. So the energy will be not wasted like the conventional vehicle. The brakes will keep braking the vehicle, thereby generating a lot of heat, right? But for this car, the energy can come back from the motor, then store in the battery.
Okay.
So I have a question.
Yes, please.
Anybody doing research on using nickel iron batteries for power source?
You mean the nickel battery?
Yeah, the old Edison cells.
Yes, the battery. I think that battery is about 7 volts, right?
Yeah,
no,
something like that.
Yeah.
Because Jay Leno has a 1918 Baker, and Thomas Edison put the original battery pack in, and it's still holding a charge 102 years later.
So that's called a what? Nickel metal hydride battery, is that right?
Yeah, I think so. A nickel iron.
Nickel iron. I don't know. I know nickel cadmium battery and
Yeah,
nickel
and nickel
metal.
metal hydride.
Yes.
Hmm.
That battery is good too. That battery is, for example, like a Prius. First generation of Prius use a nickel battery, nickel metal hydride battery. That battery needs a very little management system. And also is not very sensitive to the temperature.
Yeah,
So
yeah.
you don't need the design fancy cooling for that battery. But that battery has another issue, which is memory effect.
Yeah, for nickel cadmium.
Yes.
Yeah.
Nickel cadmium is already gone because of the existence of the cadmium.
Yeah.
The battery is, cadmium is poisonous.
Yes.
Yeah. So it's not environmental. Nickel metal hydride battery, usually the battery voltage cell is about 1.3 something. So yes, I mentioned 7 volts or something, but really that's multiple cells.
Hmm.
You see
So you're saying the energy density is poor?
Poor, definitely. Energy density is much lower. The energy density of a nickel metal hydride battery is much lower. This is why, people have been debating whether, the lithium-ion battery is much less safer than the nickel metal hydride battery, but still automotive move towards the lithium-ion battery because they find, okay, anyway, the size is smaller, contains more energy.
Okay, thank you. Yeah.
Sure. Okay, I think